Now that we have the rotational partition function, we can go ahead and do what we did for the vibrational partition function and ask what's the average energy for a molecule that comes just from the rotational energy levels. And again, this is just thinking about diatomic molecules. Well, the equation that we have is this is equal to kBt squared times d log q rotational with respect to temperature. All right. And so we can go ahead and plug in our value. You can look at log of q rot here. All right, q rot is equal to, so natural log of kb times t over hb. We only have one term that has t in it, so we can go ahead and sort of separate these out. We'll have our log kb over hb plus log t. When we take the derivative, this term will go to 0. So we get d log q rot dt. It's just going to be the derivative of, with respect to temperature, of log t, which gives us just 1 over t. And so plugging this back into our original E rot expression up here, the average energy from the rotational part of the molecule is kBt squared times 1 over t, which just gives us kb times t. And so if we want to find this, for a 1 mole, if we want to turn this into a molar energy, we would just multiply by Avogadro's number. So if we were looking at a molar value, we would get RT, because Avogadro's number times kb is equal to R. Additionally, similar to the vibrational partition function, we can look at what's the contribution to the heat capacity, right? So if we take the derivative of this with respect to temperature, so I write dE rotational dt, that's equal to CV. And if we want to look at a molar value, we would do it for we would take the derivative of RT. That just gives us R. So we get a contribution of R to the heat capacity for a diatomic gas from the rotational energy. Now there's one final wrinkle that I just want to make sure to mention with the rotational partition function. Everything we've derived up to this point only applies to heteronuclear diatomics. There's one extra term we need to add for homonuclear diatomics. So the more correct version, or the final version of this, is that Q rotation is equal to the temperature divided by the rotational temperature, and we have to add this extra term sigma. Sigma is equal to 1, which is what we were just looking at for a heteronuclear diatomic, meaning that we have 2 different atoms as part of our diatomic, something like HCl. Sigma equals 2 for a homonuclear diatomic, where we have 2 of the same atom that compose our molecules. So something like chlorine or nitrogen would require this extra term. And this is due to symmetry. So this is known as a symmetry factor. We won't really get into all the reasons why this is. It's just good to know that this is an additional thing that applies when we have the symmetry of a homonuclear diatomic like nitrogen or chlorine. Okay, and that concludes our section on the rotational partition function. We'll just have one more video sort of summing up. If we take all of these different parts of the partition function, what does our total partition function look like for a molecule?